Here in Online Lecture 7, we'll be looking at a few different mapping techniques, beginning with dosimetric. Before we begin by talking about dosimetric, let's talk about some negatives of choropleth maps. One of the negatives is that the data that is within that particular geography, let's say a county or a state, it's not uniformly distributed within that particular county or within that state. What do I mean by that? Well, we think about things that are uniform distributed in a particular county. The Marion County tax rate, that's something in which it's uniform across the county. However, where people live in Marion County, that's not uniform. Obviously, people don't live in manufacturing facilities. They don't live heavily in agricultural areas of the county. They don't live on the White River. They don't live on Eagle Creek. They don't live in park areas. There are certain areas where people do not live. Further, space is not uniform. In the case of Indiana, we've got 92 counties. That's a ton of counties. However, none of them are the same size and shape. And I return to a previous map that we've seen, and here's population of Indiana counties in 2020. And so, once again, not everyone in Marion County. It makes it seem like all throughout this particular county, the population is uniformly distributed. Further, let's go up here. What's the problem? We know that there is a lake that comes right through here. So obviously people don't live there where the lake is, here in Lake County and Porter County. Going even further, down here, we know that most of the people live near the Louisville metro area. You go way out here, hardly anybody lives out here. But it makes it seem like, because this whole entire area is shaded a certain color, it makes it seem like the population is spread out and is quite populous throughout this whole entire area. So that's a flaw. Earlier I asked, is space in Marion County, is it uniform? No. And so we have different areas, different land cover classifications. Open water, obviously people don't live there. Areas where cultivated crops is happening. Yeah, there might be a farmer in a small house or big house, whatever house it is, but it's a small number of people. It's, they're not going to have subdivisions, neighborhoods like you would see in these higher dense developed areas. Forested areas, they might have people living there, but not in the same numbers as you'd find in the developed areas, the areas that are shown in red. And so in the case of Marion County, what previously we saw was population is uniformly distributed. Not so fast, my friend. That we know that is not the case. So this gets us to two problems, not only with choropleth mappings, but just more in general that we see with spatial data. And so I want you to read the excerpt called The Pitfalls and Potential of Spatial Data. In there, it talks about two things, the Modifiable Aerial Unit Problem, or MOP, M-A-U-P, and the ecological fallacy. The Modifiable Aerial Unit Problem, further, I got plenty of examples to showcase this, but the idea here is the aggregation of data at different scales and resolutions can produce the problem different results. And so if what determines the results of a particular map or our particular research is how we draw the geographies, then really is that doing anything? It's more just a lesson in geography than a lesson in your data. Another thing is the ecological fallacy, and the idea there is effects observed at different scales can be different. And the example there we think of as crime rates in particular counties. We say, well, low-income counties have higher crime rates. That means low-income people are more likely to commit crimes. That's a fallacy. What you're doing is you're using group, essentially, information and trying to apply it to the individual. And that's a problem we see beyond cartography, beyond geography. Here's two visualizations of what I mean when we think about changing the geography. And so here, the modifiable aerial unit problem, we have, in this case, smaller grid cells, in this case, higher grid cells or larger grid cells. And so this is a finer resolution. This is a less fine of a resolution, more coarse resolution. And so subsequently, we could get different results. And I'll show an example of this here in a minute. Another way we can think about as how we draw lines is, going beyond just grid shapes, and this, how we have, different counties, different shapes, different, townships, different geographies have different shapes. And so we were going to get different results based on how these lines are drawn. And so these are arbitrary lines. These are man-made, human-made lines that are drawn on top of a map and essentially separates different geographies, different groupings. So it's all just a lesson in lines and where they're drawn and where they're not drawn. Another way to showcase this is here. Here we have 9 grid cells. N equals 9. 9 cells. I added them all up. The mean is 8.8. Now let's change this. And so here we have, let's say, these 2, the yellow, these 3 green, and then these 4 combined. And so now I have new sums, new data here. And so all this particular 4 squares, the average is 11.25. And so now n equals 3, and now I have 3 groupings, yellow, green, and purple, or yellow, green, and magenta. And now notice how it's actually changed the mean. The mean of this entire area has subsequently changed. And it's all because of how I essentially have now aggregated up. So I essentially have bigger geographies than I did beforehand when I had smaller geographies. And here's an excerpt from that particular reading that I've asked you to do. And this is where kind of thinking about, once again, changing the shapes, changing our particular geographies. And so here we saw the regression is 0.69, and this typically happens as we aggregate up, as we start using larger groupings of geographies. Essentially is what it's going to do is it's going to find a greater relationship between the independent and dependent variable. And so it's going to be kind of, it's a little deceitful. I mean, it's not really being honest there as we start to change the geography. And so here we can see, now if we go this way, so taking boxes, grouping them like that, actually has even a higher linear regression. So this is how, if you want to, if you're doing research, you want to have a high R squared, you can play around with the geographies. And so this is, once again, the modifiable areal unit problem and a pitfall of spatial data. And there's a political geography term often associated with the MOP. And if anyone can guess it, you got 5, 4, 3, 2, it's gerrymandering. And perhaps you recall earlier in the semester, we actually looked at maybe thinking about different geographies. In that case, we use hexagons. Perhaps that may be a better way to think of this. Instead of having these these randomly sized, some small, some big geographies like census tracts or townships, if we use something consistent like a hexagon, maybe that might be more fruitful or a solution to the modifiable areal unit problem. And in this schematic here, I kind of try to explain the ecological fallacy. And so here we have groups. So we have groups of information, but we know that there's individuals. And so if I went to this particular home and say, well, hey, you live in this particular area, that mean you're a high income, wealthy individual. And over here, this is a very, very healthy area. So you must be super, super healthy. We know that that's a fallacy. Yes, group information is useful. We can kind of see trends, and we can see, understand some spatial patterns, but we know that at the local level, at the individual level, things can vary. So it's a fallacy to think that everybody or everything located within a geography behaves as that is represented on a particular map. I've read this before. Breaking news alert. Countries that consume more coffee have less cases of heart disease. How is this a fallacy? Well, here I am right now. Sipping my espresso that I have every single day, and I've got advanced heart disease. So that's a fallacy. So when we think about things as far as, well, it means that everyone who consumes coffee must, well, it's hiding at what's happening at the individual level. We know there's so much more going on. In my case, it's genetic. It has nothing to do with the country I'm located in, how much coffee I consume. And so that's a fallacy. And so we see this throughout research of a variety of types, including geography. Now let's talk about the purpose of this particular lecture. That's the datasymmetric or dosimetric mapping technique. This is a solution to some of the flaws I just identified beforehand in the choropleth mapping technique. The idea here is what we're going to do is we're going to display statistical surface data by partitioning space into zones where the boundaries reflect the underlying statistical surface variation. Long definition. Go ahead and write it down and kind of keep coming back to that as we flesh this out. This is a newer technique. What's kind of cool about this is when I was in cartography school, we didn't learn about this at all because without computers, you really couldn't have done this. So this is a relatively new technique. Even further, ArcGIS, it's hard to do. It doesn't have like a built-in tool in which you can just crank out these dosimetric maps. So you have to kind of play around with things, and it's hard. You got some if you know scripts, if you know Python and all that, you can figure it out. And you can also work with it to get to the destination. But the idea here is we're going to use interpolation. And that's something you're going to see coming up next in the next video lecture on isoarithmic maps. And so the idea here is we're going to require us to make assumptions, interpretations, and data manipulation. And so essentially we're going to have to kind of use computers to help us create our outcomes, create our outputs, create our particular maps. Key to a decimetric map is it takes a choropleth map and it combines it with or adds to it ancillary information. And I'll explain that here in a minute. So that their outcome then is a decimetric map. So what is ancillary information? It's extra info used to standardize the data. In our case, we're going to use land use and land cover classes of data. So examples of this: residential would be an example of land use. Water, i.e. the White River, Eagle Creek. Forest, a park. The Fort Benjamin Harrison Park. Agriculture, Franklin Township, Decatur Township, lots of ag, open fields. Those are essentially classes of data that has been identified by others, and we can do that is we can take that information and essentially use that to then take those choropleth maps and get them to a better detail, a more accurate representation of actually where people live. Because if we have choropleth maps that stretch across an entire area, we know there's a water, forest, farms. We know that that's not where they're going to be living. They're going to be living where there's people that reside. They're going to be living in neighborhoods, residential areas. And there's two different databases that we use for this particular lecture, and that's the LandScan and the National Land Cover Database. And so those are both going to be used as ancillary information that we're going to use to then make or create our decimetric map. One key thing is the ancillary information. The data must be at a finer resolution. Otherwise, you can't show the non-uniform distribution of a phenomenon. For example, let's say you have a choropleth map that's at the block group level. Your ancillary information cannot be at a bigger level, at the tract level. However, if you have a county choropleth map, you can use block group ancillary information, or like we're going to see here, if you have a tract level choropleth where it has census tracts, you can then use a 1 kilometer square spatial resolution for your ancillary information, as you'll see. Now, before I go using my Indianapolis example, I'll use essentially the origins of this. And so this is a particular website that's no longer available, so if I'm offending anybody, I apologize. But it's a good way to explain and showcase this whole idea of the decimetric mapping technique. So here are census tract boundaries for Delaware County in Pennsylvania. So each of these are individual census tracts. Now here is the data for population density. And so all those census tracts, essentially, you can create now a choropleth map that shows people per, in this case, square kilometer. And so, of course, heavily dense over there, very light over here, very light over there. So we have some cool information, some choropleth map, great. Let's take and add to that some ancillary information. So here we go. This is ancillary information. So in this case, this is land cover data. And so we have agriculture, bare, developed forest, water, wetlands. Essentially, we know that people are going to be living where it's developed. Yeah, you might have some people living out in the woods. I'm not saying there's not. I'm just saying we're more likely to see. So essentially what we can do is we can take this choropleth map and we can say, okay, can we now separate and divide it? And so we can kind of focus these big, huge tracts, focus in and put those people, put that density where people actually live. And so essentially we take the choropleth, add to it the ancillary information, and then the result of it is a decimetric map. And so now we have the same map when we're doing population density, and now we have a much finer resolution, much more accurate as far as where people actually live. So we're still using the same classes, still using the same color ramp or color scheme. However, we can see it's much more finer detail, much more accurate compared to the problem that we've identified with using big, huge census tracts, big, huge areas, is they mask, they hide the true underlying representation of where people actually live. So like I said beforehand, This is hard to do in ArcGIS, so I really didn't do this per se. I kind of played with some things to do this. So just realize that this isn't something you can do in ArcGIS cleanly, easily, without a little bit of help. But what I did was I took a population density map of Marion County. We have census tracts here from 2020. I then took that previously used national LCD land cover of Marion County. So this essentially shows where people live and don't live for the most part. Because we know over here's the airport. This is the Indianapolis airport. It's developed. We know that. It's a runway, very, very nice airport, all of that good stuff. But we know people don't live there. So you can take the land scan. What it does is it has a night population that it does of the entire country, and then separates it and kind of divides it into low density, medium density, and high density. So the high density specks there are down there in the central business district, the downtown area. The yellow, the higher density than the green. But nonetheless, we can now see that whole entire airport is now shown as being empty, which makes more sense. So let's go ahead and do our daysymmetric map. And so here now is the daysymmetric population density that combines the choropleth map with the ancillary information, being both the land cover data and also the land scan night population. I use night population because that's where people are residing, assuming that most jobs are during the day, and so most people are at night residing in their homes. So that then provides that information. Then I can then use that to create a much more accurate, much more detailed. Now, previously, we look at the census tracts. This is all big, huge area here. All this now essentially is much more finer. We know exactly where the population is most dense and where it is less dense. So if I zoom in to the southwest side of Indianapolis, we have our different census tracts. The green and the brown is kind of forest, open space. This is floodplain. So here we have the White River coming right through here. 465, obviously people don't live on the interstate. So 465, and so we have all this particular area. This is all quarry, recycling, trash, landfill, all kinds of stuff over here in which people don't live there in large numbers. And so this huge area would be all representing this entire census tract. So we know that in the case of this particular area, people only live over here or in this particular area or right there. And so we know that we can make it a little bit more realistic. And so here we can see density at a much finer resolution, much more accurate. So that's the whole idea of daysymmetric mapping. Once again, could not be possible before computers could just crank this stuff out beforehand. There's no way a human could do this, without a lot of time and I guess no social life. Real quickly, I want to talk about Landscan. It's kind of a cool global database that you can use. It's free. You have to ask for it. But what it does is a good job of showing where people reside, but also where they are during the day. What it does is uses grid cells that are approximately 1 square kilometer in area, so it's pretty good detail, pretty good resolution. It was developed in Tennessee at the Oak Ridge National Laboratory. So if you click on that link, or if you actually copy and paste that link, or if you essentially just look at that link and then put it into your browser, you can access it. It's a good data set. You should consider using it, provided you can and know how. It's kind of you got to have your GIS and remote sensing chops. Got to be able to, know how to use a lot of this data, but it is useful. What it does is it, like I said, distinguishes between where people live or reside at night, but also where they are during the day. And so it's nice to provide that, because if you think about the United States census from year 2000, only showed 55 people were located in the World Trade Center block. So of course, come 9/11, there were a whole lot more than 55 people affected. So this is important to think about for disasters when we have, maybe a tornado that might go through a central business district during 2 o'clock in the afternoon. It's useful to know where people are and where people aren't. So it's all, useful for resource management, for emergency management. For any type of disaster, for any type of situation, to know where most of the people are at a given time. What's cool about the Landscan is it utilizes a variety of information to calculate this raster of population. It kind of shows where different, low density, high density, and all of that. Uses roads. That's from the National Geospatial Intelligence Agency. Uses slope, and that slope is getting, it's very, very, very high detail, very, very accurate slope. That's via the digital elevation model. So slope is being created from LiDAR. Overwhelming LiDAR is extremely accurate. And the idea there is, people are going to live on super steep slopes. Of course, we don't really have to worry about that too much in Marion County, but the idea there is that's why slope is inserted into the land scan. Populated places, and so what this does is uses the National Geospatial Intelligence Agency land cover data, and also takes into account nighttime lights that are provided from the National Oceanic and Atmospheric Administration and their National Geophysical Data Center. And once again, here's the land scan night population for Marion County, just kind of as a refresher now I just mentioned it.